The transition elements have an unparalleled tendency to form coordination compounds or complex compounds. Complex compounds are those in which a central atom or ion is surrounded by a number of anions or neutral molecules possessing a lone pair of electrons. These surrounding anions or molecules are called ligands. Some examples of complex compounds are given here. They are pentamine cobalt 3 chloride, potassium ferricyanide 2 and nickel tetracarbonyl 0. The tendency of the transition metal ions to form complexes is due to their relatively small size and resultant high positive charge density. Presence of vacant n-1d orbitals. Their ability to show multiple oxidation states. Now let us look at the catalytic properties of these elements. Transition metals and their compounds are known to catalyze various reactions of industrial importance. The catalytic activity of these elements is attributed to their ability to exist in multiple oxidation states, which enables them to form unstable intermediate compounds. These metals also catalyze reactions by providing a suitable reaction surface. Familiar examples include the use of vanadium 5 oxide in the manufacture of sulfuric acid by the contact process. The use of finely divided iron in Haber's process for the manufacture of ammonia. And the use of nickel in the hydrogenation of oils. The table here shows the catalytic activity of some of the transition metals. Many views have been advanced to explain the mechanism of catalysis. In catalysis at a solid surface, bonds would be formed between the molecules of the reactants and the surface atoms of the catalyst. The 3d electrons of the first transition series elements are used in bonding, in addition to the 4s electrons. Thus, the concentration of the reactants at the catalyst surface increases, and the bonds of the reactant molecules weaken because their activation energy is lowered. Since the transition metal ions can change their oxidation states, they act as catalysts more effectively. For example, iron 3 catalyzes the reaction between iodide and persulfate ions by changing its oxidation state. It first gets reduced to Fe+2 by oxidizing iodide ions, and then gets oxidized to Fe+3 by reducing persulfate ions. Now let's look at the formation of interstitial compounds by these elements. Interstitial compounds are compounds of indefinite structure and composition. They are formed by the incorporation of small atoms like hydrogen, boron, carbon, or nitrogen in the spaces between the metal atoms, that is, the interstices of the lattice. The component elements of these compounds do not combine in definite ratios. Hence, these substances are also known as non-stoichiometric substances. For example, Fe0.940, TiC, Mn4n, Fe3H, VH0.56 and TiH1.7. Note that the formulae do not correspond to any normal oxidation state of the metal. The important physical and chemical characteristics of these compounds are: they are extremely hard. Some borides approach diamond in hardness. They have higher melting points than those of pure metals. For example, titanium carbide melts at 3683 Kelvin and titanium nitride melts at 3473 Kelvin. They are chemically inert. They possess good electrical conductivity. Let's look at the alloy formation by these elements. Pure metals have poor mechanical properties. Hence, they are not used as such in industry. The properties of the metals may be modified by adding other elements. Alloys are one such class of compounds. An alloy may be defined as a homogeneous mixture of a metal with other metals or metalloids, and sometimes even a non-metal. The atomic radii of the transition elements in any series are not too different from each other. As a result, they can very easily replace each other in the lattice, and thus readily form alloys. Alloys are classified according to the components in two distinct types, namely, ferrous and non-ferrous. Ferrous alloys contain iron, carbon, and one or two of the other elements like chromium, vanadium, tungsten, and molybdenum. When the content of carbon in an alloy is less than 0.1%, it is called an iron alloy. When the content of carbon is more than 0.1%, the alloy is called a steel. Depending upon the other elements present, steels are classified into several types, like vanadium steels having vanadium, chromium steels having chromium, and so on. Non-ferrous alloys are alloys that do not contain iron as one of the components. The number of non-ferrous alloys used in technology is very large. Aluminium alloys like aluminium bronze, duralumin, and gamma alloy, along with magnesium alloys like magnalumin and electron, find numerous applications in various fields. Similarly, brass, an alloy of copper and zinc, and bronze, an alloy of copper and tin, are also important non-ferrous alloys. The table shown here lists some important ferrous and non-ferrous alloys along with their composition and uses. Potassium dichromate is one of the most important compounds of chromium. It is prepared from its ore, chromite. The preparation of potassium dichromate from chromite involves 3 steps. They are preparation of sodium chromate, conversion of sodium chromate into sodium dichromate, conversion of sodium dichromate into potassium dichromate. Let us see the process in detail. Finely powdered chromite ore is mixed with soda ash and then roasted in a reverberatory or rotating furnace in excess of air. The mass turns yellow due to the formation of sodium chromate. The sodium chromate solution obtained in the first step is filtered and treated with concentrated sulfuric acid and gets converted into sodium dichromate. On concentration, the less soluble sodium sulfate crystallizes out. This is filtered hot and allowed to cool, after which the orange-colored sodium dichromate separates on standing. A hot concentrated solution of sodium dichromate is treated with a calculated quantity of potassium chloride. Potassium dichromate, being less soluble, crystallizes out on cooling. Now, let us look at the properties of this compound. Potassium dichromate is a crystalline ionic solid with a very bright red-orange color. The chromates and dichromates are interconvertible in an aqueous solution, depending upon its pH. Even weak acids cause the yellow chromate to change into the orange dichromate, while it is reversed, adding an alkali or a carbonate solution. The structures of the chromate and the dichromate ions are given here. While the chromate ion is tetrahedral, the dichromate ion consists of 2 tetrahedrals sharing one corner with a CR-OCR bond angle of 126 degrees. Sodium dichromate is highly soluble in water and is widely used as an oxidizing agent. Potassium dichromate is preferred to sodium dichromate for use in volumetric titration. This is because the sodium compound is hygroscopic, while the potassium compound is not. Thus, potassium dichromate is used as a primary standard in volumetric analysis. In an acidic solution, potassium dichromate furnishes nascent oxygen. In other words, the dichromate ion accepts electrons and thus acts as an excellent oxidizing agent. For example, acidified potassium dichromate oxidizes ferrous sulfate to ferric sulfate, hydrogen sulfide to sulfur, halogen acids to halogens, and stannous salts to stannic salts. It also liberates iodine from potassium iodide. Let us now see some important uses of potassium dichromate. Apart from being used as an oxidizing agent, potassium dichromate is also used in chrome tanning in the leather industry. It is used as mordant for dyeing and in the volumetric estimation of ferrous salts, iodides and sulfides. Potassium permanganate is the most important and well-known salt of permanganic acid. It is prepared by fusing pyrolusite ore or manganese dioxide with caustic potash or potassium carbonate in the presence of atmospheric oxygen or any other oxidizing agent like potassium nitrate. The reaction produces dark green potassium manganate, which disproportionates in a neutral or acidic solution to give potassium permanganate. In the laboratory, potassium permanganate is prepared by the oxidation of a manganese 2 salt by peroxodisulfate. Industrially, it is prepared by the electrolytic oxidation of a manganate solution. In this method, the manganate solution is placed in an electrolytic cell provided with a rotating wire netting anode. An inlet pipe made of iron for the liquor acts as the cathode. The oxygen liberated at the anode converts manganate into permanganate. The purple solution containing potassium permanganate is evaporated under controlled conditions. Potassium permanganate then crystallizes out. Let us now look at the properties of potassium permanganate. Potassium permanganate forms dark purple, anhydrous, needle-like crystals that are isostructural with potassium perchlorate. It is moderately soluble in water. On heating strongly, it decomposes into potassium manganate, manganese dioxide, and oxygen according to the equation shown here. The structures of the manganate and permanganate ions are shown here. Both these ions are tetrahedral. Pi bonds are formed by the overlap of the p orbitals of oxygen with the d orbitals of manganese. Note that while the manganate ion is paramagnetic due to the presence of one unpaired electron, the permanganate ion is diamagnetic. Let's now look at the chemical properties of this compound. Potassium permanganate acts as a powerful oxidizing agent in acidic, alkaline, and neutral solutions. The effective equations in each of these media are given here. Let us see some important oxidizing reactions of this compound in each of these media. In an acidic medium, it oxidizes sulfides or hydrogen sulfide to sulfur, sulfur dioxide to sulfuric acid, sulfides to sulfates, nitrides to nitrates, arsenides to arsenates, oxalates or oxalic acid to carbon dioxide. Ferrous salts to ferric salts, iodides to iodine, hydrogen peroxide to water and oxygen. In a neutral or fairly alkaline medium, it oxidizes manganese sulfate to manganese dioxide in the presence of zinc sulfate or zinc oxide as catalyst. Potassium iodide to potassium iodate. Sodium thiosulfate to sodium sulfate. Nitrotoluene to nitrobenzoic acid. Let's now study the uses of potassium permanganate. Alkaline potassium permanganate is used in organic chemistry under the name of Bayer's reagent. Apart from being used as an oxidizing agent in the laboratory, it is also used in the volumetric estimation of ferrous salts, oxalic acid or oxalates, and hydrogen peroxide. Qualitative analysis for the detection of halides. Bleaching of wool, cotton, silk and other textile fibers. Decolorization of oils.